Okay, it's on. All right. So the topic for today's lecture is cascades in networks. So we're going to talk about a few different models that deals with a propagation. Again, it's propagation on the network, but we're going to look at on it from a slightly different angle. So far, we mostly worked with the viral propagation model, the one where there is a certain probability of a propagation of virus from one node to another, right? Based on the strength of this viral infection. We're going to talk about slightly different models today, and we're going to talk about what's called threshold models. And these models, they are more geared toward different type of information, different type of propagation, and we're going to talk about it right now. And then we're going to consider a very practical model, very practical approach, which is called influence maximization, where we looked into selecting optimal nodes within the network to maximize the influence, right? To maximize the effect of the propagation. So, as I said, there are pretty much, you can think about two different types of propagation. One, what we call a viral propagation. And, typically it's virus, infection, rumors, news. So these are the situations where there is no, the recipient, right, the recipient node does not have any, does not participate in some sense in this propagation, does not make any decision, in the sense that, like, nobody asks me if I want to get a virus, right? You're in the contact with somebody who is infected. Well, there's a chance you're going to get it, right? I might not ask somebody about rumor, but somebody told me, well, I heard it. So it's not in the control of the receiver, of the agent. There was a different setup where the agent, right, the node in the network, actually makes certain decisions, right? And in this sense, the propagation is under the control of the node, right? Now, what I'm trying to say is the following examples. For example, you're considering buying I don't know, new iPhone, right? Never-ending story of buying new iPhones. Well, yes, there is, of course, some iPhone properties that you take into account, but it's also, might be your friends. All of them have new phones, and so they influence you, right? You're making the decision, but you're being influenced by your surrounding. The same situation with joining political protest. Whether you're going to go onto the protest or not, participate in it or not, will depend, on your friends. And, each of us might have different threshold. For somebody, it's enough. If somebody doesn't care and can just go out, doesn't matter what happens. Somebody else might think that, look, if half of my friends join the protest, I will also join, right? So there is a threshold. The same kind of scenario can be applied to adopting of innovation or changing somebody's behavior with respect to technology, right? Switching to a new technology based on the innovation. Again, let's say, even if you, I don't know, even if you're in love with, like, sort of with computers without internet, right? Eventually you realize, and you can kind of get and share information through, like, used to be CD-ROMs, DVD-ROMs, USB ports. Slowly but surely, that way of sharing information goes away, and you pretty much, if you're not online, you just cannot get anything on your computer. And at this moment, for example, Macs does stop even putting CD drives or anything else. Not even standard USB ports there anymore. So, you kind of forced to adopt innovation if you want to change the information, exchange information with others. So again, your decision You're making the decision, but it depends on the decision of the surrounding people. Finally, there is yet one more situation where you have a network, and you probably heard about those cascading failures. And typically it happens with electric grid, where part of it fails, and then the failure propagates. And if one of some part of the, say, transformers fail, then others, like neighbors, start getting higher load, and then they fail, and then they fail and fail and fail, and sort of there is a cascade of failures. Now that happens because, again, neighbors fail. So the state of the neighbor change depends on the state of its neighbors. And so in this sense, there is this threshold model, and we'll talk about a few of those where the state of the node will change depending on the state of the neighboring nodes, right? And so that's sort of that's overall the model, the approach. Okay, so now let's look at a few stories. Now this, in fact, there's sort of this separation between, information spreading and action has been, studied for a while within economics theory. And, we first will take a look from, this models from economics perspective. And then we'll go and sort of switch our heads and go to computer science world and look into, modeling and simulations that are done more on the computer science perspective. So this is kind of motivational study that's used in economics to sort of motivate, to confirm that there is this really two different processes that's happening. One is information spread, and the second is actual action or adoption. Now this is a study of hybrid corn adoption in US in 40s, 30s, 40s. The story there goes that the hybrid corn is actually much better than the corn that they used to plant in US. When that corn was introduced to the market, the manufacturers, of course, thought that everybody will jump on it, but it didn't happen. And then the study is actually, it was a longitudinal study through many years. And what they were like literally asking farmers is, have you heard about this, right? About this sort of new, better corn? And well, have you adopted it, right? And so there was this huge delay in between actually hearing and adopting. And what you see here in this histogram is just the number of those who adopted. And during those interviews, farmers would say that, like, look, yes, why did you adopt? Well, my neighbor adopted and it showed good results. And so pretty much it was literally sort of propagation on the social network, propagation of information, where people learn about something and maybe learn it from the neighbors. And then the propagation of, when you have to make an action, right? Where you need to decide whether to, plant that corn or not. And it also depended on the neighbors. And there are many more stories. Another famous story is actually with penicillin, how it was, spreading. The same if you talk to doctors, how they prescribe new medication. It's kind of goes through the friendship network, and you realize what others prescribe. So how can we model this? And why is it different? If we look at this very simple picture, this graph, imagine that, think about the virus propagation model we talked before, and think about this node, for example, V, this node being, let's say, infected. Well, let me get it colored. Let's say this node is infected, or any of those nodes are infected. Well, it's a matter of time that the infection will jump onto this node W, right? And whether we want, there is a certain probability that is going to happen, right? And you wait long enough, it most likely is going to happen. So if there is a breach, infection will cross it sooner or later. Now, in a decision-making model, the situation can be quite different. If, for example, we decide that node W will change its behavior only if 50% of his friends or neighbors change the behavior, one node, doesn't matter what it does, will not be able to affect the behavior of this one, right? Again, think about this, and this example, we're going to talk about it many times. Think about, say, competing mobile networks, right? So, you have mobile, you have mobile phone, and in Russia, okay, we have MTS, Beeline, Megaphone, right? And so, usually within this mobile networks, the cost of for the call within the network and the cost of the call for outside network, they're different. And so it might be beneficial for you to actually, switch and to be on the same networks with your friends, right? The more friends, you have in the network, the cheaper it is for you, right? So, imagine then that this W node, belongs to one network, and this V node, for example, belongs, switches to another, like this is MTS, this is Megaphone. Now, for W, I mean, yeah, it's going to cost you to call this guy V, but you still have more guys on your network, so it would make sense to switch to another network just because one of your friends switched. And so just single edge is not going to make W change its behavior or switch. And that's the difference in between this sort of threshold model, where you do need critical threshold for something to happen, versus the sort of the information propagation model, the one as we described before. Does it make sense? Okay.
Yeah.
Okay. So as I said, as I mentioned before, this type of logic comes from economists, right? And they do like, think about interaction in terms of game theory, for example. And, on the networks, it's actually called local interaction game. And the idea is the following, that if you have, two nodes, A and B, and there's sort of two players, right? And, if both of them adopt similar behavior, they both benefit from it. If they adopt, similar behavior, but sort of different type of behavior, they also benefit, but there is sort of different, different costs, different payoff of adopting the behavior. And if they adopt, opposite behavior, they get zero payoff. In some sense, again, if you think about this as this mobile operator scenario, yes, if you both belong to the same network, it's cheaper. Belong to a different network, it might be also cheaper, but sort of differently cheaper, right? So it's different payoff. And if you're on different networks, well, you don't get any benefit out of it, right? Of course, you can, instead of like having positive payoffs, you can put costs and make them go negative here if you want. So then the idea, this sort of network coordination game, or what's called direct benefit, is the following, right? So there is a node B, and it has some number of friends that follow behavior A, and some number of friends follow the behavior B. And node B has to make a decision whether to follow behavior A or behavior B, right? If both behaviors would give you identical benefits, then the answer is obvious, right? So if the both behaviors give you identical benefits, sort of what's in for this picture, what should node B do? Which strategy follow? Which strategy should he follow?
It may be B, but it depends on the values A and B. I mean,
exactly. So yeah, it depends on the payoffs. But if, for example, A is equal to B, right? If the payoffs are the same, then the obvious answer is strategy B. It has to join these guys. But if the payoffs are different, then you can actually sort of try to find that balance, right? By computing the total payoff you're going to get. Say if you're getting payoff A from from each connection, well, then there is the this a p portion of type of certain type of neighbors, right? And then that the total number of neighbors, well, you know, you can easily write this expression and you can calculate a threshold, right? And so the threshold would be threshold for accepting, for example, behavior A is when, you know, your number of neighbors, I'm sorry, when the threshold in terms of the fraction of the neighbors to accept this behavior is, you know, b divided by a plus b in terms of the payoffs, okay? And again, if a and b are equal, then the threshold is half, right? So you need to have half nodes to behave differently, you know, to make sense of switch that. Now, that actually leads to a very, you know, it's extremely simple local model, but it leads to a very interesting consequence in terms when you look at how this behavior spreads across the network. Let's try to take a look at this. Let's say, you know, this is underlying network, and let's say, you know, a equal 3, b equal to 2, right? There is this sort of, remember, the payoffs for joining, you know, one or another. And let's say we're right now on the behavior, you know, type B, switching to behavior type A. And the threshold has to be here. If we do this, the threshold has to be, you know, 2/5, right? So that's b divided by a plus b. Now notice, if we have just one node, node W, that has this new behavior, for each of its neighbors, it is, say, for example, we take this neighbor, it's only one out of his 3 neighbors. And so it's 1/3. But the threshold is 2/5 of the neighbors need to have this behavior for the node to switch. So this node, you know, will not want to switch. You know, this node will not want to switch either, neither this, neither that. So, you know, if this guy switches his behavior, nothing happens. He's only one. Now, imagine that these 2 nodes switch the behavior, right? There's these 2 guys. Again, think about this as, you know, megaphone versus, you know, MTS. Those 2 guys decided to move on. Now something interesting happens. If you look at the node S, he still has only one neighbor of this new behavior type, and so it's below threshold, below 2/5. But for node R, this is actually 2 out of 3 neighbors, right? So it's 1, 2, 3 neighbors. 2 of them are already on the new behavior. So based on our threshold, it's 2/3. 2/3 is greater than 2/5. So for this node, it makes sense to switch, right? Well, yeah, it's a coordination game, right? It makes sense to coordinate with neighbors depending on their status. Now, one thing which is important here, we kind of making it progressive or sort of one-way street, right? We're not allowing to switch back. Right? Okay, so node R is going to switch, and of course, node T is going to switch. Now, what happens on the next step? On the next step, this node sees that, look, there is 1 neighbor, 2 neighbors on the new behavior, and only 1 neighbor on the old behavior. So for him, it also makes sense, right, to switch to new behavior. And so then it switches. So bottom line, if we take this type of model and the payoffs are like this, let's say, you know, Megaphone gives you better discount than MTS for calls, for internal calls, right, within the network. And this is a picture of sort of a friendship. And this is, you know, again, there are like lots of assumptions here, right, obviously. And this is the communication channels, and they're sort of equal intensity, blah, blah, blah. But then switching those 2 guys will actually make, you know, economically, from economic sense, for each of their agents, if they're reasonable, they have to switch, right? And they'll switch in turn, you know, following this picture, right? So it's a cascade that propagates through the network. Does this make sense? Okay. Now you can, by now you can kind of realize that this this is actually a very, very practical problem, right? So if you think about, viral marketing, well, that's sort of the math behind it, how to actually do this. Okay, now, if we look at slightly different scenario, let's look at this picture. And again, let's keep the same, that's the same payoffs, 3 and 2. So it is sort of more profitable to be on the new one. And let's start this process from those 2 nodes, pretty much doing as we done before. We realize that after a few iterations, maybe not instantly, but after a few iterations, these guys will switch. But then something happens. This influence will not spread out anymore because it cannot get in here, because for this guy, it's only 1 out of 3. It cannot get here because it is 1 out of 3. This is 1 out of 5. So that's it. It's stuck. So, what you observe is that within this model, if you have thresholds, this influence might get stuck. And that also means you can actually can set up a mathematical problem of influence maximization, which is, okay, how do you select nodes such that it will give you the largest possible cascade size, right? Maybe if you pick up not these 2 nodes, but you pick up originally, these 2 nodes, and I don't know the answer, but maybe if you picked up these 2 nodes, the cascade will be larger, or maybe smaller. I don't know. Or maybe you pick up this node and this node as the seed nodes. Well, then it's probably will not go anywhere. But the idea is how to pick up the right nodes to maximize the size of the influence. All right. Now, again, keep in mind that this is, it's not a sort of, first, second, or third Newton law, which is, the way the nature works. This is a model, right? And sort of it's within this model, the results that we're seeing. Now, how well this model describes the reality, that's sort of slightly different story.
I have a
So,
story, about previous slide. So I understand if you go step by step, okay, it's stuck, but actually in global, the optimal strategy where the all nodes in some one group, the most cheaper, I mean, in one strategy or not?
I'm sorry, I probably don't understand. You mean switching everybody in one step, or?
No, switching everybody in one group, I mean, in one strategy. I mean, no, in your example in MTS.
You know what? I'm not sure I'm understanding you. If you want, we can switch to Russian for a second, or I'm not sure.
Я имею в виду, почему не является самой оптимальной стратегией просто перевести всех участников в одну группу? Ну, то есть...
Okay. Yeah, so the idea here is the following. Imagine that, so the question is, why do we actually, think about all the strategies? Why not to switch everybody in the same group, like right away? I mean, the answer is the following. Imagine that you're building a marketing strategy and you need to convince people to switch, right? The way you typically convince people to do something, if you're, doing this, if you're, say, mobile operator, is giving them freebies. For example, I'll give you a free I'll give you a free iPhone if you switch to MTS. Will you switch? Most likely, yes. But the marketing budget is not infinite. So then the question would be, okay, I have this maximum, I have that much money I can use to convince people to switch to my service. I can do a few things. I can either evenly spread it and give it to everybody a little bit, but then for each person, that would not be enough to switch, right? To convince them to just switch. So I can do something different. I can actually find some people and I can give them much more money, each of them, right? Much bigger benefit to make sure they're gonna switch, and then try to see this viral propagation of the switching, because then their neighbors might not, will not get freebie from the network, but because of their usage, for them, it will be more beneficial to switch anyway because their friends switching. Does this make sense?
So your point is it is cost to switch. We have some cost to switch each node to some.
Right. Yes. So what we're trying to do is we're trying to see like if we can, with the smallest number of sort of direct investment, if we can make the largest change to the network, right? Using this network effect. So that's the idea. I mean, overall, the idea would be like, okay, you can formulate the problem in two ways. One way is with this number of nodes I can afford to switch directly, how big of the cascade can I get? Or, and then you just try to find those nodes, right? Or you can say, I want to have that side of the cascade. How many nodes do I need to influence to actually get that, right? All right, so this is sort of, but this is, again, this is kind of on a you know, it's game theoretic and kind of sort of, it looks like a game, right? Where you play this sort of agent-based models that economists love. Now, let's look at sort of.
May I ask about this model?
Sure.
While we didn't go further. So can we use this for community detection? It seems like if we will choose some of the nodes which are in the same community, then it's kind of like a random walk. We'll stuck in this community because for others, they have a lot of friends in other community and few friends in this one. So it's hard to propagate to them. So if we have assumption, 2 people in this community and we switch them to new strategies, then we find the community.
You're actually right. It is very close, and you could potentially use it as a community detection. So in fact, you know, it is absolutely correct that these cascades are being, you know, stopped within the communities, right? They're getting stuck in the communities, and you know, it's. You will see in a second, you know, the algorithms, you realize that algorithms are quite expensive to build, you know, to solve exactly this problem. And so typically community detection algorithms are cheaper than this. So often people kind of go other way around. They say like, let's detect communities. And then we kind of know that within tight community, this information and this, I'm sorry, this cascade will propagate within the community. And so they don't model it anymore. They just say, okay, you know, if there is a community and we seed it, then it's gonna, you know, switch, the entire community will switch. But you're right. I mean, this is very, this is very close, right? The difference is, again, with community detection and random walks, we typically talked about the sort of probability. And here we said, okay, there is this hard threshold that allows things to propagate or not. But you know, again, you know, what you're saying is correct. It's you know, that there is a direct you know, this influence does not usually get out of community. In fact, it's also true in the opposite thing, that for this type of influence, it's very hard to get into community, which actually means that's why you know, all those, say, you know, organizations, right? All those, you know, terrorist organizations or any, you know, sort of hardcore religions where people interact much more with the people within the same community, it's very hard to pull the people out from that, right? Because they have very little interaction with outside world. And so this influence cannot propagate, spread in there. Because, you know, if you're all of your friends have a certain belief, right, there is no chance you're going to switch beliefs. All right.
Thank you.
Yep. So there are, now again, guys, compared to Newton's law in physics and mathematics, this is not like sort of some fundamental ground truth, but these are a couple models that have been proposed and actively used, right? And then we're going to talk about those couple models. So in fact, they've both been summarized in the paper, actually very influential paper by David Kempe, John Kleinberg, and Eve Tardash, 2003. They looked into 2 different models, I mean, 2 different types of activation. One was what's called this sort of linear threshold model, which is on the right, and this is the one we talked about, which activation means the following. You need to have certain number of, neighbors of certain type of behavior for you to switch the behavior, right? So threshold. The other option, which reminds you about about the spiral models, is that you kind of have this diminishing returns, which is the probability of activation is proportional to the number of activated neighbors, right? And proportional, well, not necessarily linear, it can be some sort of nonlinear function, but the point is, the more of your neighbors are active, the more chances that you'll become active, right? So the difference is there is a threshold here, there is no threshold here. So some of the sort of effects slightly different, but both models can be used for simulation, right? So this one, even with one single neighbor that switched, gives you some probability of switching. This one, for example, on this picture, until 60% of your neighbors switch, nothing happens, right? Okay. Now, typically, in math, these models behave nicer because, they're differentiable. This does not. But if you do simulation, both works, and it's sort of nicer. This one more from a econometrics perspective, kind of like, okay, there is a threshold. Okay. So, how does this work? Well, if we look at the first model, which is this independent cascade model, right? It's this one. It's, again, this is a paper that called it that way, and so it kind of, in literature they call it that way now. So we have initial set of active nodes, some sort of set of active nodes, and we run the simulation. There are discrete time steps, and in every step, an active node can activate neighbor with some probability. Okay, and that probability in this model can be different for different edges, right? So the edge can carry different weight. And if the neighbor becomes active, if the node succeeds in this activation, neighbor becomes active and stays active. And so process runs until it kind of stops. Now, if we fix this probability and keep it the same constant for all the edges, this model can mimic the behavior of SIR model, where a node stays infected only one step. So remember, in SIR, it's susceptible, infected, recovered, and when the node is getting susceptible, when the node getting infected, it can infect the neighbor as long as it is infected, right? And so within a simulation, if it stays infected, like say 5 steps or 10 steps, it can get it on every step. It can still have a chance to infect the neighbor. That's SIR model. But if in this particular model there is it's only one chance that's being given to infect the neighbor. So again, if it's P constant and it's only sort of very quick recovery, it's similar to SIR behavior. So it's a little bit more general model because of this different probabilities on the nodes, on the edges. So that's one type. That's one model that's kind of being studied.
I'm not sure I understand that last sentence on the slide. This model still works if if the node stays infected for 5 steps or something like that, right?
No. What I'm saying, the way they created this model, and again, like, oh guys, it's not sort of right or wrong. You can have your own model with slightly different properties. It's just for this model, they proved a few more things. But here, what they're saying is the following: every step, an active node can activate connector, the node connected, but it can have only one chance of doing it. So, it's get infected, right? Here it's activated.
Okay, I understand.
It can activate its neighbor,
that's fine.
but it's just sort of once. On the next iteration, it cannot do it anymore, right? you know, that's sort of the way they formulated the model. I mean, if you want to go deeper, you know, read this paper. It's actually quite a short paper, like 3 or 4 pages. It gives you more flavor on why they selected this type of model. Another model, the one we kind of literally looked at already when we talked about, you know, economics, is this threshold model, right? Where again, influence comes from the neighbors, and you need, you know, sort of each node has a random each node has an acceptance threshold, right? And you can actually either have them all equal, which is quite not realistic, or you can have them, you know, random and distributed in a certain way. For example, you know, have Gaussian distribution, so you know, there is sort of average number of nodes, but somebody might have a very low threshold, somebody might have very high threshold, right? Think about, again, joining a protest or something, right? Somebody can be very sort of crazy, go alone, and somebody will need like 90% of his friends to go in order to join. And the same situation, the same scenario, you know, initial set of active nodes, you know, iterate over discrete time steps. And again, this is a progressive model, right? So there is no sort of, you know, there is no, you know, kind of recovery or switching back, right? You kind of activate and you become active. Okay. So, you know, if it is mobile operator networks, you kind of, you know, there are several seed nodes that they switch to a new network, and then they spread their influence and other people start switching, but there's no switching back within this model. Can you model it with switching back? Yes, you can, but it's just you know, different properties. Now, here is an example, and by the way, notice this, for example, this paper is 2003. This slide is based on the work done by Duncan Watts in 2002. So before that paper, but it just tells you that, you know, as always in research, ideas, they kind of sort of in the air, and a lot of people working on them from different angles. So here is, it's this, this second linear threshold model, right? This is a threshold model. An idea here is, you know, Duncan Watts was studying how that cascade propagates in a random network, right? Remember that random network, like Erdős-Rényi network, is a very special network, right? And in that network, you can actually, you know, do a lot of things analytically. And so he actually calculated a bunch of those, you know, graphs analytically. And so the idea is the following: you can either have a global cascade, which means, you know, you have a single node or a very small set of nodes, and then you have this threshold model, and then the entire network switches, or the entire network activates, or not entire network, right? And so he called it global cascade when, you know, the entire network activates. And then if it is not entire network, it's called, you know, says no global cascade. He does not go into like here into the details of whether, you know, what would be the size of the activation. It just says it's not going to be the entire network. Okay. And so if you remember in random graphs, there is this, you know, the important characteristic here. It's called Z, you know, and I didn't write it here, but let me, let's me do it. So if you remember, the key metric is the average node degree, right? Which is a parameter P, you know, the probability that two nodes are connected times, you know, the number of nodes in the graph, right? And so here on this slide, you know, I just copied the picture from their paper. They call it Z. So it is this one, right? So it's average. So this is an average, you know, degree of the network, right? So what we have on this axis, right? This is a network properties. On this axis, you have this threshold, right? And here it's, you know, fixed threshold, exactly the same for all the nodes. And here you will get, you know, thresholds where they're distributed like Gaussian. And so what happens is the following. And I mean, you know, it's kind of, it looks like a strange phase diagram, but it sort of makes sense if you think about this for a sec. Remember, in random graphs, if average node degree is less than 1, the random graph is disconnected. There is no connected component in there. And so obviously there is no way a global cascade can exist, you know, here, because, you know, on this region, random graph is disconnected. There is no, you know, there is no connected component. And we remember that after average k exceeds 1, you start, I'm trying to write 1, you know, exceeds 1, you start getting a gigantic connected component, right? And so from here on, you have a, you know, gigantic connected component, so a lot of nodes connected. And these are thresholds, and you know, it looks a little strange with the steps, but if you think about this point to the step is actually equal to, you know, 1/5, right? So it is literally says 1/5 of the neighbors. This is 1/6 of the neighbors. This is 1/7 of the neighbors. This is like 1/4 of the neighbors, etc. And so what it says, like, look, if we look at you know, if we change the threshold on one hand, on the other hand, if we look you know, at the different networks, you might get, you know, it might get cascade or not. And the idea here is that if you're actually getting on a very dense network, right? This is quite dense network, and it's everywhere here. It's dense. You know, it's 14 neighbors. You actually have very little chances to get a cascades out. And the reason for that is because, think about it. It means every node has a lot of connections. So in order for that node to flip, right, to be activated, lots of his neighbors has to be active, you know, because we're talking about the threshold, right? So if the threshold is very low, which means very few neighbors need to be activated, yes, you can still get cascades, you know, pretty high density of the network. But if you need a lot of friends to be active, it's only in the networks that have, you know, low degrees k you can be activated and get the global cascade, right? So it just shows you that, look, there is this interplay in between the density and you know, and overall you know, activation and the size of the cascade. Does it make sense?
Yes. Did you explain the graph on the right with the sigma values?
Yeah, sigma. This is okay. This I think, and that's what I mean, this is, I might be mistaken, but I think what's here is the following. It is, you do have the threshold, and this is the, you know, average value of the threshold, but instead of just having a fixed threshold, you have a distribution, you have a Gaussian distribution, right? With this phi being sort of average.
Oh, okay.
And every node
that's the
has
variance. Okay.
different, yes.
Yeah, that can make sense.
Okay.
Or the standard deviation.
Yeah, okay. Guys, this is again very short paper, very short, sweet paper. You know, take a look. It will explain you all the details. Okay. Okay, let's move on to sort of the next part of the topic. Now, you know, this is just an example of how, you know, you can actually simulate this on the network, and you know, depending on your seed nodes, you know, you might either sort of inflame the entire network, or you know, it might not go far out, right? Depending on the network structure. So this is just sort of visual. Okay, so let's get back to the mathematical problem. So now we see how the influence spreads. So let's formulate this strictly. So what we want to do is, let's say we have an initial set of active nodes, A0, and we want to calculate the cascade, the size of size sigma, right? So sigma of A is number of active nodes when propagation stops, right? So in this case, we have active nodes, 2 active nodes, and the size of the cascade is 1, 2, 3, 4, 5, 6, 7, is 7, okay? So for those, so, you know, A0 here are these 2 nodes, cascade size is 7, right? So the problem is find k set of nodes that produces maximum cascade. So here, for example, if I have, you know, k equal to 2, the question is, you know, find the 2 nodes that gives me maximal cascade. Here is an example. We selected these 2 nodes. This is a cascade we got. Now, maybe again, if you select node 10, I mean 11 and 12, you get larger cascade, maybe smaller. Or maybe if you select node 2 and node 13, you'll get larger cascade. And it's called maximum influence problem, right? And this is maximum influence nodes. Now, it's sort of, you know, obvious in that this is, you know, the usual sort of, the usual integer programming, integer optimization problem. And, you know, it's going to be NP hard because you literally have to go through all the possible combinations, right? So think about this. If I want to find the maximum, right, to maximize this, I'm actually trying just to get some light going into the camera. If you want to, you know, find the optimal set, what do you have to do if you actually just approach it in like in sort of constructive manner? Well, you know, you pick up one node, you look up, you know, let's say you have 5 nodes you need to pick. So you need to go through all the possible combination of these 5 nodes to, and for each of the combination, you need to calculate the total influence, right? So it's clear that it's sort of, if you have, you know, 100 nodes, your initial set, that's impossible, right? So the question is, how can you solve this? And, you know, for those particular models we discussed, they possess, those 2 models that we discussed, they possess a very interesting property. And because of that, you can actually prove that a very simple algorithm can be very efficient in solving this problem. Now, if you reformulate those models, right, you know, you don't like something about them, and you reformulate the models, you know, this approach might not work, the approach in terms of finding the optimal set, right? But for those 2 models, in the paper, it has been proven that this works. Okay, so the idea is the following, and before we jump into this, the idea, there is a sort of, it's called submodular function, which, you know, submodular is the notion of monotonicity. If you think about, it's about, if you deal with the set functions. So the idea is the following. Imagine that you have sets, you know, S and T, and S is a subset of T, right? So, I mean, it's probably worth, I don't know, why didn't I draw it? You know, you have a set S, and you have a set T, and S is a subset of T. And then the point is the following. If you take a few other nodes, and here is sort of nodes V, and you add them, you know, you consider them, adding them to subset S, right? So S plus V. Then the total influence, the additional influence, marginal influence they're going to bring will be higher if you add them to the smaller subset than when you add it to the larger subset. So again, so the marginal improvement of the function, if it is if the function is submodular, right, by adding the nodes, here is larger for the you know, smaller set, for the subset, than comparing to adding it to the entire set. If, you know, here we're looking just at the sizes of those sets, but this is the idea again. If you have smaller subset, adding to it will actually give you more effect than adding the same nodes to a larger subset, to a larger set. In other words, let's say you have 5 nodes and you add 3 more nodes to it. The effect, well, this function f, submodular function, will have a larger effect adding those 3 nodes than if you had 15 nodes and added 3 nodes to them. Right? I'm not talking about the size. I'm talking about the effect. You know, the definition of what submodular is. Does make some sense. So the idea, of course, is that the cascade size function is submodular, right? So that's sort of the reason we're talking about it. And that's what the authors proved. But there is now the reason we're talking about this. Why would we care that this cascade thing is a submodular function? So it is submodular. So what, right? The so what answer is the following: that if you have monoton submodular function, and we're trying to maximize it, and that's what we're trying to do in this in our models, right? Then the greedy algorithms actually works pretty well. So let me explain, how it works, and then explain this, inequality. Imagine that you have, somehow an optimal set, right? And let's project it onto our problem. We're trying to find the set of nodes of fixed size that maximizes the influence. Now, imagine that you found it, right? Imagine that you have it like the perfect set. Then the value of the influence is f of that set. So that's the size of the overall cascade. Okay. But we don't have magic, so we don't have the set. But let's use some process to build a set that we think might be good. And the process is the following. We're going to repeatedly just include the node that produces a marginal increase. So here how it works. You go through, let's say we're starting with empty set. We need to pick up the first node. So what we do is we go through all the we go through all the nodes in the network, and we start our influence propagation from each of the nodes. And then we pick up the one that gives us the maximum influence. We fix it. Then we pick up second node, and with those 2 nodes together, we measure how far the influence would go. And we pick up the second node that gives us the largest improvement compared to the first node, right? The marginal largest improvement. Now we have those 2 nodes, we fix them. Then we go for the third one, and we go through all the possible third nodes, right? And for those three together, we see the influence, and we pick up that with this 3 gives us a maximum, etc., etc., etc. Right? Make sense? So you're not going through all the possible combination of multiple nodes, but you fix. It's a greedy algorithm. You select the best first. Then for this best first, you select the best second. Then for those 2 fixed, you select the best third, etc., etc. Right? So it's a greedy optimization. Now, typically, with greedy optimization, you never know, right? You can get stuck in local minimum,
sorry,
local maxima. You never know how it's going to work.
Do you hear me?
Yeah.
I have a question.
Yes.
As I understand, in the first iteration, we need to check all possible nodes.
Yes.
And the second iteration, all possible -1 nodes.
Correct.
Okay.
Yes, absolutely. Yes. So you pick up the first node. You start with you go through all the nodes one at a time, and for each of them, you compute how far the influence would go from this node. Then you select the one that gives us the maximum influence. You fix it, then you check, go through all the n-1 node, right? And see how far together with this first one, how much influence, you're gonna get. And you select the one that gives you marginal largest increase, right? And then you fix it, and then you go for the third, et cetera, et cetera. So, but again, the amazing part of this, that for submodular functions, you can actually prove that this greedy algorithm will give you the result not worse than 1 minus 1 over e of the optimal, which is, I think it's 67%. So with this greedy algorithm, you get to 67% of accuracy of the optimal solution, which is actually very good. Can you do better with some other algorithm? Maybe, but this kind of guarantees it. And now kind of going back in the logic, for those formulations that we did for those two models, the threshold and linear cascade model, it can be shown that those functions are submodular. And since they are, this theorem applies, and so you can actually solve that maximization problem by a simple greedy algorithm, right? Versus, if you pick up any other model, you can either, you can try to show if it's submodular or not, or you can actually, try to invent some other algorithm that, that will work. And again, it just sort of intuitively, right? You'll have to go through, if you want to have the maximum, so maximize the set, you have to go through all the possible combinations, which is a very large number, right? Okay. Now, and by the way, this is, this factorial large, it's a problem if you have a, large initial seed set, right? If you have 100 people, then, selecting 100 out of the network of 1 million, that's a lot of work. If you say, I want just one node, well, you can probably do it because, you just do it 1 million times and that's it, you're done. Okay, so the cascade size is a submodular function for those type of models that we talked about. And literally greedy algorithm allows you to, get to this level of accuracy, right? So the set that you found, gives us, it will be the size of the total influence will be greater or equal than 62%. And in practice, it's actually even better than that. This is like sort of the bottom, the low guarantee. So this is the algorithm. And, it's greedy optimization. So we're trying to do, we're trying to find maximum influence set. We set up with a set, it's empty, and then we go through all the, nodes. And as I said, adding the one that gives us marginally large improvement. And then just keep iterating.
K is the number of iterations. It defines like at the beginning.
Oh yeah, K, yes. K is the number of nodes you want to have in your set, right? So you can say, I'm trying to find, a set of size 5, right? Make sense?
Yes,
yeah, I mean, you're right. Somebody corrected me that 1 minus 1 is 0.632, right? So, and I said something else, yeah. So it's 63%. Yeah, I wonder. I'll check it. All right. So here's an example. The authors, did the algorithm. I mean, they ran the tests on the algorithm. They took the collaboration graph, 10,000 nodes, 53,000 edges. And so here is the idea. this is that K, the target set size, sort of how many nodes you target, right? You activate at the beginning. And this is how big of overall active set size you get. Now, this collaboration graph is not very dense, and of course, you know, the answer, you know, the answer here depends on the structure of the graph, and of course, they run multiple sort of experiments. And the point is, the way to read this is that if you take, you know, say initially 10 nodes, and you run this algorithm, you know, you will activate 40 nodes, right? And if you take, you know, 20 node set, it eventually activates 60 nodes. Interestingly enough, if you take 10 nodes and you run sort of random selection, so if you pick up those 10 nodes randomly and run the model, you know, your size of your cascade is 10. So, and it's kind of intuitive, right? Because you realize how it works. So if you pick up randomly, there is very little chance they're next to each other, and so there is very little chance that they will you know, activate any other node, because, you know, if nodes have more on average than 1 degree, then having just one neighbor active is not going to activate the node. And so these are different algorithms. You know, they just showing literally that, yes, that their approach behaves better. Now, if you remember, from the previous module, we also talked about, you know, different properties of the nodes. And for example, you know, you might think that there is some heuristic that might work. For example, you can select as seed nodes, not just sort of random nodes, but the nodes with a high degree. Okay, I mean, that's you know, that's a good heuristic. I mean, you know, if you want to, if you think about like spreading the news, for example, you know, you might want to select the guys with the largest number of connections. Here, it does not necessarily work, because if you realize the nodes with high degrees, they usually, and remember that's the way we also learn it in this network structure, they usually connected to the nodes with also high degrees, right? So somebody with a lot of friends usually have connected, their friends are also, you know, well connected. So which means if you select a node with a high degree, then, you know, to activate its neighbor, but the neighbor also has a lot of connection. And then all of a sudden, you're one of the lot of connections, and that's not enough to activate that node, right? That's the logic. You know, in this sense, it's better to activate some nodes that are maybe not the that have not the highest connection. But they tried various experiments. They tried to activate nodes that are, you know, the most central nodes that have higher degree. And I mean, you know, it definitely works better than, you know, random, right? It works better. You can also try to activate nodes with the largest eigenvalue, you know, with the largest page rank. You know, it works better. And honestly, if you think how much this algorithm costs and how much it costs you to just pick up random, you know, maybe it's worth just, you know, forget it all and just, you know, pick up, actually not random, but how much it costs you to pick up like high degree nodes. You know, maybe it's worth just picking up high degree nodes. It doesn't give you like this level of result, but it's definitely better than just picking up random nodes. Okay, so it's, you know, it's a heuristic. Now, this algorithm by itself, you know, this independent cascade, for example, model, if you think about its complexity, it's at least you know, think about this. We need for let's say we need to get k nodes, right? For I mean, the size of the set is k, right? We want to like say fine, you have 5 nodes that are initially infected. Then I need to go, and I mean, I need for each of those, I need to select this node from all the nodes, right? And so you know, for the first one, yes, I need to go through n nodes. For the second, n minus 1, third, n minus 2, n minus 3, but k times n pretty much. And then for each of them, I need to to run the simulation in terms of the size of activation. And that simulation pretty much on average should touch, if it is global cascade, it should touch all the edges. If it is not global, it should touch part of the edges, but it's sort of order of number of edges in the graph. So you're getting on this sort of number of nodes times number of edges. Even if it's sparse graph, number of edges, approximately the number of nodes, so it's n squared at least, right? So it's expensive. If the graph is very large, n squared is a lot. So then there were like lots of different improvements people tried to make on this, and here there was a paper where the guys tried to just run very different. They actually did, they were focusing on two things. One is influence spread, so how far the influence would go, and the other one is, the other parameter is, how long it takes to actually compute. And here is for them the seed set size, and again this line, which is far at the bottom, this is random if you select it random, and then this is sort of the pretty much the best sort of hardcore original algorithm with some improvements. And then there are a bunch of algorithms where you mix up this maximization idea with some heuristics, right? So again, you take random, it's very fast. You take degree, it's a little bit slower, but still pretty good. And then then you can try to do, there's this whole bunch of different modifications to this influence maximization algorithm, and the computational time, running time. So every time you pretty much need to decide if going for the highest influence, right, worth the computational time. And if the graph is not very large, it's probably worth it. If graph is very large, then it might be better off using some heuristic. And that's, by the way, coming back to this question you had before. Can you use it to detect clusters? Well, yes, but if you remember, the best clustering algorithm is actually of order of m, and this is n times m. So yes, you can. But it's quite expensive way to do it. So yeah, and that's pretty much it here. I forgot to mention here, there's a paper that started it all on action viral marketing. And then it's Pedro Domingos, and I forgot the second author. I'll add it here. And then the sort of the key contributions here. The paper is by John Kleinberg and David Kempit. It's maximizing the spread of influence and influential nodes in diffusion models. These where those models coming from. So, bottom line, this is quite. I mean, this problem, usually causes a lot of interest, in business, because the viral marketing, everybody talks about it. And the ways to select the most influential nodes seems like a very good thing to do. Now, if you think about this, and challenges in this model, I don't remember right now, but probably like Megaphone, MTS, they have what, like 50 million, 150 million, I don't remember the numbers, but they have a lot and a lot of, pretty large customer base. So the graph of 50 million, it's not easy to run those type of algorithm on that big graph. So then you probably need to like sort of partition and do play a lot of tricks. But at the same time, it gives you, it's very, I like this kind of this approach because it's very clean mathematical setup, and it's very clear what we're doing. Okay, any questions?
A question about greedy algorithms. You said that it's working when we have some modular function.
Yeah.
And are there any cases when these greedy types of algorithms will work with the high probability?
Man, I don't know. I mean, probably. I mean, look, usually the whole point here is, if you think for a second, not about sets, but any other function, right? The question is, what's the sort of the cost function look like, right? If there is like a lot of maxima, minima, regis in there, then the greedy algorithm by itself most likely will get stuck, and then you'll never reach, any good solution, right? And in fact, that's what we observe even with, say, when we compute the modularity and many other algorithms. So the answer there is, run multiple iterations and try to restart and get where, try to get the best out of those. So the answer is, I mean, I don't know. There might be some algorithms that achieve this, but if there is not, the solution would be to just run multiple iterations, right? And that will allow you to, not to get stuck in local minima, right? But the sort of beauty here that there is this guarantee, right? Typically with with greedy algorithms, you just don't have a guarantee at all, right? And so you're kind of acting on it experimentally.
Thank you.
All right, okay, guys, that's it for today. Then I'll see you in a week.
I had a question similar to Ilya's. So people have tried first finding the communities and then building or choosing their influencers from the community clusters?
Yes.
Kind of like the opposite. Oh, okay.
Yes.
So people have
yes,
tried that.
People tried that. Again, you can Google for like this influence maximization problem, right? It pretty much has a name now, right? Yeah. It's sort of influence maximization, and there will be definitely algorithms, and I mean, it's sort of intuitive thing to do, right? To find the communities, and then spread it, do this influence maximization within each community, for example. I mean,
it just is one of the competitions for the second project. The first competition is actually this one. So.
All right, try it.
It's easier if you can just follow someone else's research.
All right, guys.
One more question.
Oh yeah.
You said see you in a week. Does it mean a Thursday or Saturday? As it was.
Oh. Let me double check with my other schedule, and then I'll let you know. But does Thursday work for you guys?
Yeah, it will work. Thank you.
It works better.
Yeah,
it's okay.
In theory, we have machine learning right before this, but this week we didn't.
So Saturday is better.
Yeah.
I'm quarantined. Doesn't matter to me.
Okay. All right. I'll let you know. Let me check. I'll need to check with a couple other things, and I'll let you know. All right. Okay. All right. Have a good one.